In this video, we're going to discuss autonomous equations. So autonomous equations are first-order differential equations in which the independent variable does not appear explicitly in the function. So we have some derivative of the function x with respect to t is just equal to some function of x over on the right-hand side. It turns out that if c is a critical point of dx dt equal to f of x, then x equals c is a constant solution of the autonomous equation, and we will call that an equilibrium solution. So let's just go ahead and try to figure out what's going on here with an example. So let's consider the autonomous equation dx dt is equal to x times x minus 1 times x minus 2. The first thing we want to do is find all equilibrium solutions. Well, according to this statement up here, this is just the critical points of our equation. So x equals 0, x equals 1, and x equals 2. Now, we're going to make a sketch of the tx plane. All right, t is our independent variable, x is our dependent variable. But let's make a sketch of a different graph first. We're going to make a quick sketch of the f of x plane, the x comma f of x plane. Now this is interesting here because this is our dependent variable and this is the derivative of our function. Right? So this is our function and this is the vertical axis is now the derivative of our function. But that's exactly what the kind of graph we have here, right? We have this x, which is kind of acting like our independent variable now, but is truly some function of t and is our dependent variable. And then we output the derivative of that function x with respect to t. So let's draw this graph. Well, this is a cubic with critical points x equals 0, 1, and 2. A cubic should look like this. So what we want to do with this information is recognize that our derivative is negative in this region. Our derivative is positive in this region. I'm drawing an arrow to the left to represent derivative is negative, an arrow to the right to represent the derivative is positive. Negative, positive. Okay, so now what are we going to do with that information? Well, I'm going to come over here and we're going to draw a solution, or draw several solutions in now our tx plane. Now this is truly what we want, right? T is our independent variable of the function x, and now we have our function x along the vertical axis, so our dependent variable or our output value along that vertical axis. This is a lot more standard to what we're used to seeing when we graph equations. So let's see what's happening here. Well, this thing out here is actually called the phase line. We're going to draw something called the phase line here. We're going to put our critical points, x equals 0, 1, and 2 along this line. And then we want to rotate this x-axis, right? So our derivative is going up from 2 to infinity. So I'm going to draw an up arrow here, draw a down arrow here to represent that between x equals 1 and x equals 2, our derivative is going down. Here we have another up arrow. Guys, between 0 and 1, our function is going up, or our derivative is positive, so that means our function is going up. And then we'll put it down here. Down arrow here. Okay. Now, what can we do with all of this information? Well, we want to draw our equilibrium solutions. So each of those x equals c lines is an equilibrium solutions. X equals 2, x equals 1, x equals 0. And all of those are solutions to the differential equation. Now, we want to draw other solutions in between each of these. Well, how do we do that? So given some initial point here, we know that this function is going down. So these graphs are going to look something like this. And what that tells us is if we have any initial value here, t equals 0, x equals 1.5 maybe, then our solution will look like this. Our solution to the differential equation will look like this. This question, part 2 up here, actually only asks us to draw one other non-equilibrium solution between each pair of equilibrium solutions. I just drew 3 in here to give us an idea of what's going on. I'm just going to draw 1 for each of the rest of these. So this tells us our function is going up because our derivative was positive. So it looks like that. This tells us, again, our function is going up because our derivative was positive. So we'll get an we'll get a non-equilibrium solution that looks like that. And this is down, so this moves away. So if we have an initial value that places us in between each of these equilibrium solutions, this is roughly what that non-equilibrium solution will look like. And so now we've graphed part 2 that was asked about. We want to determine intervals of x such that non-constant solutions are increasing or decreasing. We've already done that here. X of t is increasing from 2 to infinity. So x of t is increasing on the interval from 0 to 1 and 2 to infinity. This is in terms of x. These intervals are intervals in x. And x of t is decreasing. Where is that decreasing? Well, it's decreasing from negative infinity to 0, union 1 to 2. All right, and then part 4. Well, actually, we're going to fill that out up here. This says to classify each equilibrium solution as stable, unstable, or semi-stable. So the definitions of those. A stable solution is if all of the solutions, or the solutions around it, converge to that point. So notice x equals 1. All of the, if we start at any point in between 0 and 1, or 1 and 2, we notice that our function is approaching this solution up here. So x equals 1 is a stable solution. Notice at x equals 0, we get a function that goes away, and then a function that goes away above it as well. So this is an unstable solution, as in if we get off of this point at all, then the solution is going to tend away from here. And this one up here is unstable as well. Semi-stable would occur if one side was approaching and the other side was moving away. All right. And so that's how we answer part 4 here. So that was actually part 4 there. Okay. And that is it for that example. We have one more example we're going to do. Okay. So we're going to consider the autonomous equation, x minus 1 quantity squared. So first, find all equilibrium solutions. Well, this is just x equals 1. Part 2, we are going to draw our f of x function. And this is x minus 1 squared, so this looks like this. And I'm going to draw an arrow to the right and draw an arrow to the right for each of these because our derivative is positive here, right? F of x represents the derivative, right? This is equal to f of x is what we're going to call that. So our derivative is positive. Our derivative is positive over here. So now let's draw our tx plane. And we have one equilibrium solution at x equals 1. We have our phase line over here where this is going up, i.e. our derivative is positive, so we're drawing an arrow that goes up. Okay, I'm going to draw our equilibrium solution. If we start somewhere down below, what's going to happen is our function is going to increase and then approach 1. And if we start above x equals 1, our function is going to move away from x equals 1. So here's our picture of the tx axis. And we want to determine the intervals of x that a non-constant solution x of t is increasing or decreasing. Well, x of t is increasing. X of t is increasing from negative infinity to 1, and union 1 to infinity. And furthermore, the last thing is to classify each of these equilibrium solutions as stable, unstable, or semi-stable. Well, on one side we are approaching the solution, on the other side we are moving away from the solution. So this solution is semi-stable. And that concludes our video.